Welcome everyone. Today we'll be exploring the inner workings of any normal computer, focusing on the fundamental components and workflows. We'll start with an analogy to help understand the basics of how computers operate. From there, we will dive into something we call machine code and demonstrate how this maps onto the so-called von Neumann architecture, that is, how a computer actually does its work. From there on, we will flag some of its limitations, specifically the bottleneck between memory and processing. Finally, we take a look at how modern processors address these issues, helping optimize performance in computing tasks. By the end of this session, you'll gain a clearer understanding of how modern machines work and how we can leverage this knowledge for performance optimization. Let's dive in. To begin, let's consider a simple analogy. Imagine a person sitting at a desk with limited space. This desk represents the core of the computer. On this desk, there is enough room for 3 sheets of paper, which we call registers. These registers are where computations occur. The arithmetic logic unit, ALU, operates on these registers, performing tasks like addition or multiplication. The ALU can combine 2 sheets and write the result into one of them again. So for example, if I write 3 on one sheet, that's one register, and write a 4 on the other register, I say add, so it gives me a 7, that has again to be written onto one of these papers. The third register is the so-called program counter. We will revisit it in a minute. The main memory on the other side is like a giant filing cabinet filled with sheets of paper. Each sheet contains a value and they are organized sequentially and enumerated. When we perform computations, data is brought from the main memory to the desk, that's our registers, processed, and then returned to main memory. This cycle of moving data back and forth is central to how computers operate. For example, when adding 2 vectors, the data for the vectors is stored in the main memory, so every sheet contains one value. The first entry of each vector is fetched, added together in the ALU's desk, and the result is stored back in memory. This process is repeated for every element of the vectors. The code that tells the computer exactly what to do, that is, how to move things around, how to hold them in registers and so forth, is referred to as machine code. It holds only the fundamental operations that a computer can perform. It retrieves 2 pieces of data from the main memory, processes those values, either by performing calculations or making comparisons, and then it stores the result in another register before returning it to the main memory. As the machine code is only a sequence of instructions, we also call it instruction stream. Let's look at this example. At the top of the screen, you can see a C code snippet. This code computes the scalar product of a vector of length I. Now, what happens when you use a compiler is that the high-level code that you write is translated into something that the computer can understand. That's the machine code. In this example, I've included pseudocode to illustrate how such a program might look at the machine level. What you see here is essentially a long sequence of instructions stored in the main memory. In a typical von Neumann architecture, the machine type we are discussing, both the instructions and the actual data are stored together in the same memory. Alongside that, we have registers, labeled as A, B, C, D, that are the paper sheets we have been talking about. So this time we have 4 registers rather than only 2. And then we have one more register that we call program counter. When you start an application, the entire program is transferred from the disk into the main memory. The program counter then is set to the very first instruction in this block, which in our example starts at location 0. The CPU, or the arithmetic logic unit, ALU in this case, begins by fetching the first instruction. For instance, this first instruction is load 50. The program counter is updated to point to location 50 and the execution jumps to that part of the program. So the program counter is really just another register, but it instructs the computer what instruction to read next. Implicitly, the computer increments it after each step and this way reads through the instruction stream one by one. At location 50, we might have an instruction like store 0 to register D. This corresponds to the C code at the top where we initialize f equals 0. Essentially, we are loading a value of 0 into register D. Once this is done, the program counter increments, which means that our next instruction is at location 51. This instruction tells us to store register D into location 20 into the main memory. As you read through the pseudocode, you'll notice that it processes the entire for loop step by step. This is essentially how a computer operates. It repeatedly fetches instructions, performs operations on data, and writes the results back. The key takeaway here is that every computer program, no matter how complex it appears, boils down to this repetitive process of fetching, processing, and storing data. Finally, the example highlights why we prefer writing in high-level programming languages like C, Fortran, or something more abstract, instead of dealing directly with machine code. High-level code is not only simpler to write, but also far easier to maintain. Writing and debugging at the machine level would be very tedious and error-prone. Our notion of what a computer looks like was introduced by John von Neumann. It consists of 4 components. The main memory stores data. The control unit is the mastermind or conductor which orchestrates all the other machine parts. The arithmetic logic unit, ALU, is the only part of the machine that can run calculations. The bus finally connects all of these components, including external devices like network cards or screens. This is all we need to literally run any program. It is super flexible as well, as no behavior is hardwired. We can even alter the instruction stream while we read from it. This architecture has a major limitation, the von Neumann bottleneck. The bottleneck arises because the computer is permanently busy with loading registers from main memory and putting data back from registers into the main memory, which is slow. We will stumble across this problem multiple times. Modern processors have significantly more registers than early computers, hundreds instead of just 4 or 8. Nevertheless, the number of registers is still limited, requiring frequent data transfers between registers and main memory. These transfers are slow and the key contributor to the von Neumann bottleneck. When we study GPUs later on, the number of registers would be even bigger, but the fundamental issues remain the same. For a lot of applications, it is important to understand that individual components in a computer system operate at different speed. For example, the arithmetic logic unit sometimes runs slower than the CPU. Doing the heavy lifting in calculations means that we produce a lot of heat. That heat can damage the system, so we have to downclock that part. The main memory is even slower by magnitudes than anything in the CPU. One interesting feature of modern systems is their ability to dynamically adjust the performance. For instance, the boost mode allows a computer to temporarily increase its frequency, provided thermal constraints don't prevent it. Essentially, if the system is cool enough, it can speed up. However, if all cores are running or there are many floating point operations, the thermal stress increases significantly, and in such cases, the system will clock down to prevent overheating. As memory is relatively slow, the CPU often has to wait for data. We have previously sketched the von Neumann bottleneck, meaning that we have to fetch data before we can compute and then wait until the data has come back. In reality, things are way worse. We issue a fetch, but then we have to wait multiple steps in the CPU before this data actually arrives, as the memory cannot deliver that quickly. In this context, it's also important to note that not all operations require the same amount of time. While the system is based upon clock cycles, with speeds measured in gigahertz, complex operations often need multiple clock cycles to complete. Clock cycles means steps in our introductory model. For instance, adding two floating point numbers might take 8 or more clock cycles, whereas only comparing two values bitwisely is much faster and might complete in one step. So, although a computer's gigahertz rating is often advertised, it is not a reliable metric for performance. Instead, a better indicator in scientific codes is the number of floating point operations, flops, a system can perform per second. If your code involves predominantly floating point computations, measuring flops gives a clearer picture of how fast the system will execute your program. For science, you really care about the number of computations. For performance, you then have to worry how many of those you get done per second. And here it suddenly matters if you wait a lot for the memory, or if the instruction stream has some flaws, or if some instructions need a lot of cycles, while others are quick. Even this metric is not perfect. There are different floating point formats that are relevant to different applications, but can run at different speed. We will see this in the context of AI. They often are okay with really inaccurate precision, but get a lot of floating point calculations per second out of the machine, whereas physicists or engineers care a lot to which degree the outcome is spot on. To wrap up today's session, we've delved into the inner workings of modern machines, starting with the foundation of von Neumann architecture and the challenges posed by the bottleneck between memory and processing. We discussed the vital role of the registers, the ALU, and memory, highlighting how they interact with some computations. In addition, we explored some ways in which modern processors manage performance, particularly through techniques like boost mode. Obviously, this is only one out of many techniques. We have also dipped into the importance of measuring floating point operations, flops, to better understand computational efficiency. Key takeaway is that you understand how an architecture maps a complicated program, like our vector product, onto very primitive steps, and how these steps are realized through different machine parts. Thank you for your attention. See you in the next session.